How high could we build future skyscrapers? Since biblical times, humans have been obsessed with erecting super tall buildings. The race is never over. In barely 2 years, the world's tallest structure was completed 3 times in New York City: the 282.5-meter Bank of Manhattan in 1930, the 319-meter Chrysler Building a few months later, and the 381-meter Empire State Building 11 months later. Since then, the period of architectural horse racing and ego boosting has only escalated. After a 7-year stint as the world's tallest, the 509-meter Taipei 101 in Taiwan dethroned the 452-meter Petronas Towers in Kuala Lumpur in 2003. The Burj Khalifa in Dubai surpassed Taipei 101 in height in 2010, rising to 828 meters. Although the Burj Khalifa is still the tallest building in the world, many buildings are anticipated to rise far above it in less time than it took for the Burj to go up. As humans advance, the height of buildings will continue to increase. With plans to create skyscrapers as tall as Mount Everest, it seems the sky is the limit. But how high could our future skyscrapers actually reach? Let's find out. Many urban planners project that by 2050, more than 6 billion people will live in cities. In regions where developing outwards isn't an option, building up is the only way to keep up with the growing density. Building taller always presents new obstacles and a not-so-subtle race for architecture companies to have their names associated with the tallest structures. Almost as quickly as one building is labeled one of the world's tallest, another one is designed and takes the title a few years later. While the sky is the limit, how does this affect project constructability? And what marvels of building technologies and materials would allow us to build into the clouds? A building consultant or skyscraper expert will tell you that several constraints prevent buildings from going even higher. Materials, human comfort, elevator technology, and most significantly, money all factor into how tall a structure can or cannot be. But there must be some physical constraints that would prohibit a skyscraper from rising too high. We couldn't, for example, construct a structure that reached the moon because, in scientific words, the moon would collide with the structure, causing it to collapse. But could there be a penthouse in space, outside the Earth's atmosphere, or a 100-mile-tall structure? Or a 1-mile structure? How high can we build before oxygen becomes an issue? The Council on Tall Structures and Urban Habitat, a body interested in and focused on the phenomena of skyscrapers, yes, they exist, recently questioned some of the constraints of tall buildings. Tall buildings have a variety of mechanical and structural difficulties. How long will visitors have to wait for an elevator to take them from the foyer to the 200th floor? How will megatall structures endure both predictable and unpredictable environmental forces? These difficulties are addressed by hacking existing contemporary materials and systems and developing new ones to serve an inventive building sector. The capacity to retain construction materials close to the site is one of the key difficulties when building tall structures, as the building's footprint and the surrounding region are often tiny, especially in metropolitan locations. This complicates the construction of framing members since precast panels are frequently hauled to the site as they are finished due to their inability to be stored. Many contractors, however, are now adopting a tilt wall building procedure, which allows them to pour and assemble the panels on site before lifting them into position using a crane. Skyscrapers are also considering steel alternatives, but as a building's height increases, its weight becomes a concern. Aluminum provides a lightweight alternative due to its simple extrusion technique, which allows it to conform to a wide range of shapes for practically any design. It also responds effectively to stress from internal structural elements and external pressures, such as quickly changing temperatures and earthquake seismic disturbances. Carbon fiber is another lightweight building material with long strands linked to produce a fabric-like structure. As a result, it is substantially stronger than steel, allowing it to be used in buildings subjected to high-impact loads. Carbon fibers are already being used in precast concrete components. By incorporating the mesh into the concrete mixture rather than standard steel mesh, the total weight of the structural unit is reduced, allowing it to be securely hoisted into place and fastened while retaining considerable structural strength. Ideas for what the future of concrete may look like are even more far-fetched. For hundreds of years, concrete has stayed substantially unaltered. While it is incredibly durable, Many people advocate for new alternatives since it remains a significant source of CO2 emissions. Some researchers are investigating bioconcrete, which has the potential to cure its cracks by incorporating limestone bacteria and can extend the life of concrete by up to 200 years. Even wood, which seemed unlikely to be employed as a significant structural material in a mega-tall construction, is finding new life in cross-laminated timber structures with equal strength to steel. Sumitomo Forestry, a Japanese design business, has disclosed plans to create a 350-meter-tall wooden skyscraper in Tokyo to highlight the capabilities of timber. The concept of a skyscraper constructed of wood is strange, as there are several reasons why the material should not be used. Durability and flammability are two of the first that spring to mind. Other considerations include the poor sound insulation provided by wood and its lightweight. The upper floors of Norway's Mjøstårnet Tower had to be built of concrete to give weight to the building, so it didn't sway too much. Taller skyscrapers are on the horizon, and construction materials and processes are rapidly catching up to enable these mile-high aspirations to become a reality. The primary issue is in the elevator and transportation system, says Adrian Smith, architect of the world's current highest building and the kilometer-tall Kingdom Tower in Jeddah. However, William Baker, the leading structural engineer at Skidmore, Owings and Merrills, has more insight on the matter. The buttressed core system is a three-winged spear that provides stability, usable space, and little loss of space for structural parts. According to Baker, the buttressed core concept might be utilized to construct towers considerably taller than the Burj Khalifa. Buildings with sunken bases are one suggestion for a new system. Consider the Eiffel Tower, suggests Tim Johnson, the chairman of the Council on Tall Buildings and Urban Habitat, as well as a partner at the architecture firm NBBJ, and he says any tall building would have to be like a supersized version of the Parisian icon, or the lower floors required to support the gradually narrowing structure would be far too large even to fill up. Johnson worked on a project in the late 2000s for a Middle Eastern customer, creating a structure a mile and a half tall with 500 stories. The design team found between 8 and 10 inventions that would have had to occur to construct a structure that tall. Johnson defines inventions as entirely new technologies and materials, as opposed to innovations. Pushing human inventiveness was one of the client's criteria, he explains. Johnson believes the design may have worked with those technologies and the hollow Eiffel Tower-like foundation. The project was canceled due to the late 2000s real estate market meltdown. We demonstrated that it is physically and even programmatically feasible to construct a structure a mile and a half tall. If someone had said, "Do it 2 miles," we probably could have done it as well. Johnson adds, much of it boils down to money, and who has that type of capital? Others believe it is conceivable in terms of structure as well. An idea from the 1990s for a 2.5-mile volcano-looking super tower near Tokyo dubbed the Exceed 4000, which looks comparable to the Eiffel Tower. The Exceed 4000 or Skypenetrator was never built for several reasons, the most obvious being that real estate in Tokyo isn't cheap. If this excessively large skyscraper had to be steady, the base would suck up a lot of space. According to conceptual renderings, the base of this skyscraper would have stretched for hundreds of miles, nearly like the base of Mount Fuji, which is roughly 225 meters smaller than the Exceed 4000. A structure taller than a mountain looks absurd. However, it is completely plausible. You could get higher than the highest peak if you stretched a broader and wider base. In theory, a skyscraper may be created that is at least 8,849 meters tall, 1 meter higher than Mount Everest. According to these theoretical estimates, the mountain's base is around 4,100 square kilometers, a massive footprint for a structure, even one with a hollow core. However, given structural systems, such as the buttressed core, the base would likely be smaller than a mountain's. Because structures are significantly lighter than solid mountains, this imaginary highest skyscraper could reach even higher than 8,849 meters. The Burj Khalifa is composed of around 15% structural and 85% air. Based on some calculations, if a structure is just 15% the weight of a solid item, it might be 67 times higher and weigh the same. Theoretically, a structure might reach approximately 59,000 meters without outweighing Mount Everest or collapsing the ground underneath it. We still don't know what the world's tallest structure could be. Meanwhile, Everest +1 is the highest point on the planet, but like the ever-shifting crown for the world's highest skyscraper, this estimate might rise with further examination. What do you guys think is stopping us from building even taller structures? Let us know what you think in the comments below.